In our previous video, we showed that groups of order p squared, where p is prime, are all abelian. And so what would be an interesting video is to see what happens when we take the prime and cube it. Is it also abelian? So we're going to look at that today. If you haven't seen the previous video, I will put a link in the description and in the card up above. Look at that video. We proved that all groups of order p squared are abelian. So here we're going to show, hopefully, that p cubed is also abelian for every group. Now, remember from your logic that if we're proving something true, we prove it's true for every case, right? Every group of order p cubed must be abelian for this to be true. So if we find a counterexample, that means that it's not true that groups of order p cubed are all abelian. So really, we're going to prove this to be not true. We're going to do so by a counterexample. So we just need one counterexample, one group of order p cubed that is not abelian. So a good place to start would be the smallest prime we can think of. So let's let p equal 2. So then p cubed is 8. So we're going to look at groups of order 8. And this will give us a place to start. Now, you could list groups of order 8. That's a rather tough prospect, but there are some famous or obvious places to start. And I've done a video in the past on dihedral groups. I will link to that. D sub n, dihedral, oops. Let me write that better. Dihedral groups. So the convention that I use is I put the subscript as the number of elements in the dihedral group. Some books you'll see do 2n. So here n would be 4. But we're going to look at the dihedral group, D8. If you don't know what a dihedral group is, again, watch this video. I will put the link in the description and a card above. The dihedral group is a list of rigid symmetries that are closed under composition. And like any great group, they have inverses, they have identity elements. They're closed, of course. The composition is the operation here. So let's look at, we're going to let R here, just the element, we're going to think of R as an element, be a rotation by 90 degrees. You could think of this as pi over 2 rotation. We're going to do this. Remember, the subscript here is informative because 2n, n is the number of vertices or corners, or however you want to say it. I think of them as vertices. So we have 1, 2, 3, and 4. So we have a square. We're going to say this as a square. And we're going to do rigid symmetries on the square. And we're going to rotate. So what happens if we rotate 90 degrees? So let's do that first. One rotation of 90 degrees. These aren't all going to look like squares. They might look like rectangles. I'm drawing by hand here, of course, so bear with me. So a 90-degree turn, we'll put 1 here, 2 here, 4 here, and 3 here. Right? It just takes it and turns it. And then if I do it again, so in other words, I'm rotating it twice by 90 degrees. So now I'm going to send 1 here, 2 here, 4 here, and 3 here. Let's do it again. And I got 1 here, 2 here, 4 here, and 3 here. So we're going to keep doing this until we get back to the original square. And that's exactly where we are now. And this is r to the 4th. So 4 rotations give us identity. So this means that R4 is identity. Identity will be this, that the rotations or reflections, which we'll see in a second, do nothing. It leaves the square unchanged. So if we list the reflections here, we see we have r squared, r to the 3rd, and r to the 4th, which is just identity. So a good way to write this is r squared, r cubed. And this will be all the rotations. Now remember that this is composition, so when we say r squared or r to the 3rd, we mean the compositions composed with each other. So 3 compositions is R3. I'm spelling this out so that we get a sense of what the elements are, and then I'll show you that it's not abelian. So let's let S be a reflection by the vertical line through the middle of the square. So I mean this line here. And so how many of these will we have? Well, if I reflect it once about this line, I get 2, 4, 1, 3. And if I reflect it twice, in other words, apply S twice, I get 1, 2, 3, 4. So S squared gives us symmetry back to the first square. So S squared is the identity element. So D sub 8, the dihedral group, is a collection of all of these elements that we have. We won't list E twice, of course. So we have E, we have a reflection, we have 2 reflections, we have 3 reflections. Now we have S squared, which is just E. But how do we make sure that we don't have duplicates? Well, we know we have S. It's going to turn out that we have this. And I will show a presentation of this group after we are done. But my contention is that these are the elements of D sub 8. So the dihedral group is the identity, nothing happens, 1 rotation, 2 rotations, 3 rotations, 1 reflection. Then the composition, reflection, rotation, reflection, rotation squared, reflection, rotation cubed. And those will be the 8 ways that we can rigidly move this triangle or this square. Okay. So every element here can be represented, if we think about it this way, as S, I, R, J, where, which one is which? J, no, that's I. I is between 0 and 1. That's the only options we have here. And then J will be between 0 and 3. Now, we have this, and we're going to look at the case is every composition here commutative. Now, I'm going to say it's not. And the reason I'm going to say it's not, I'm going to say that RS is not the same as SR, which, if this is true, it does not commute. It's non-commutative, which again would imply that it's not abelian. And this will give us our counterexample. So all we really need to do is look at what RS and SR do and see that if we end up with the same triangle after we do these reflections and rotations. So let's look at RS first, and let's remember that this is a composition. So we're composing R and S, and we do that right to left. So I'm going to take the triangle, and I'm going to apply S first. In other words, I'm going to rotate about that line. Not rotate, reflect about that line. I get 2, 1, 4, 3. And then I'm going to apply a rotation of 90 degrees. I'll draw the line just for reference. So we're rotating, then that puts 1 here, 3 here, 4 here, 2 here. So that's what the RS does. There's another way to write this. This is the way I like it. I like to write this as permutations on elements. And the way you can do that is you write a top line of 1, 2, 3, 4. Those are the vertices here. You can write A, B, C, D. It doesn't matter what symbols you use. And then I'm going to write where 1 ends up. In other words, what ends up in the 1 spot? Well, at the end of this, that's where 4 is. So I'm going to write 4 below 1 as a way to remember that that's where this is not writing for some reason. Apologies, there was some lag. All right, so then 2 goes to itself, right? 2 ends up at 2, so even though it travels, it doesn't really end up anywhere. Same with 3. 3 goes to itself. So after all that, 3 stays fixed. And then 4 and 1 switch. So this is sort of a permutation matrix. It tells us where it goes. 1 goes to 4, 2 stays, 3 stays, 4 goes to 1. Now let's look at what SR does. And we're going to apply this right to left, so the rotation comes first. Now you might think to yourself, well, if we're just reflecting and rotating, we should up in the same spot. You're going to see that's not true. So if we rotate, 1 goes here, 2 goes here, 4 goes here, 3 goes here, and then we're going to flip about our fixed vertical line. So let me get 1, 2, 3, 4. So what's that mean? Well, I'm going to do the same permutation matrix. And so 1 fixes itself. Even though it travels, it ends up where it started. 2 goes to 3. 3 goes to 2. And 4 stays fixed. Okay, so if we just look at the permutation matrices, in the permutation matrices, we always write the starting point on top and then where each element travels to, or permutes to, and we get this, which clearly aren't the same. So that means SR is not the same as RS. And that's it to show that this group, this dihedral group, is not abelian, because all elements must commute. So D8 is not abelian. So we found one group, D8, whose order is 2 to the 3rd. There's 8 elements in here. P is prime. That is not abelian. So it's not generally true that groups of 8 elements that, well, I should say it different. The groups of order P cubed is not abelian generally. So that's it. Counterexample, we've proven it by example, a counterexample that we found a group. It's a bona fide group. again, look at the dihedral group video I've done. I go into details of why it's a group, and you'll see the inverses and all that. Let me write down the presentation just really quick. The presentation is a way to think about the group generated by R and S, and then we write down our rules. We could do a Cayley table. I can show you where all the elements go under composition, but it's a little tedious, and I don't recall if I did it in that video or not. I think I did. No, that's not inverse, my fault. Well, S inverse and S are the same thing, but generally this is true. So that's the presentation. We can get every element we want just by this. I just promised you that. I go over presentations in that video, why they're useful. I'm pretty sure I did the Cayley table. So check that out. It's worth looking at. The dihedral groups are really important, as are symmetric groups. The symmetric groups are infinitely important in group theory. They are the queen, so to speak, of groups. I'll do a video in the future on symmetric groups. Lastly, I've been doing this lately, a sort of classification. Let's look at classifications, not of groups of p cubed, but groups of order 8, which here is p cubed when p is 2. So we already know that we found a group that has order 8 that's not abelian, but there are abelian groups that are of order 8. Let me know in the comments if you'd like to see any of these particular groups. We could just look at the groups, prove that they are groups, talk about the structure, isomorphisms, everything. So there's 3 abelian groups of order 8. Z mod 8, the cross product of Z mod 4, and the cross product of Z mod 2, I don't know where I wrote 3, by Z mod 2 by Z mod 2. So those are the 3 abelian groups, and non-abelian groups are our lovely dihedral group, D8, and an interesting group called quaternion group, which I will explain in a second here. I think I might do a video next on the quaternion group, but all groups of order 8 will be isomorphic to one of these 5 groups. Every single one. So any group of order 8, you'll see that it has the exact same structure. They're structurally equivalent to one of these 5 groups. Now, if it's abelian, you have 2 choices. If it's non-abelian, or abelian, you have 3 choices. Non-abelian, you have 2 choices. So just as a little preview, the quaternions are listed this way, and I'm not going to get too much into it because I want you to watch the next video. So this is a set that has positive and negative 1, I, J, and K. Now you might want to know what I, J, and K do. It's similar to complex number I, and that the square will always equal -1. Now, I'm not saying that I equals the square root of -1, but it's similar in this way. And then we have these multiplication rules where ij is equal to k, jk is equal to I, and ki is equal to j. So this will be a future video. Look for it. I will tie it to this because that's the second non-abelian group of order 8. We'll prove it's not abelian. We'll show the inverses We will do all the group structure and maybe some fun, interesting facts about the quaternion groups, the quaternion group in that video. One thing you should look at is the similarity between this particular group and the Klein 4 group. Now, the difference here is all of these elements have order 4, but we'll get to that in the next video. So that's all I wanted to do for this video. So maybe it's not too satisfying to know that the group of order p cubed is not generally abelian, but hey, it's fun. Anyway, thanks for watching. Let me know what you think. Like and subscribe, do all that stuff. And if you want to see quaternions, let me know in the comments. If you rather see one of these other abelian groups of order 8, let me know that too. But just comment. Okay. Have a good night.